In the continuation of the discussion, I am Christina Hangog and I'm going to discuss about considering time cost trade-offs, which include crushing activity times linear and programming model for crushing. Considering time cost trade-offs. When determining the time estimate for activities in a project, the project manager bases these estimates on the amount of resources such as workers and equipment that will be assigned to an activity. The original developers of CPM provided a project manager with the option by adding resources to selected activities to reduce project completion time. Other resources such as more workers, overtimes, and so on generally increase project costs. The decision to reduce activity times must take into consideration the additional cost involved. The effect, in effect, the project manager must make a decision that involves trading additional project costs for reduced activity time. In Figure 9.8 defines a two-machine maintenance project consisting of five activities. Management has substantial experience with similar projects and the times for maintenance activities have very little variability, hence a single time estimate is given for each activity. The project network is shown in Figure 9.14. The procedure for making critical path calculation for the maintenance project network is the same as one that was used to find the critical path in the network for both the Western Hills Shopping Center expansion project and the Porta project, making the forward path and backward path calculation for the network in Figure 9.14. We obtain the activity schedule shown in Table 9.9. Zero slack times and thus the critical paths are associated with activities ABA, the length of the critical path, and thus the total time required to complete project is 12 days. Crushing activity times. Now suppose that current production levels make completing the maintenance project within 10 days imperative. By looking at the length of the critical path of the network 12 days, we realize that meeting the desired project completion time is impossible unless we can shorten selected activity times. This shortening of activity times, which usually can be achieved by adding resources, is referred to as crushing because the added resources associated with crushing activity times usually result in added project cost. We will want to identify the activities that cost the least to crush and then crush those activities by only the amount necessary to meet the desired project completion time. To determine where and how much to crush activity times, we need information on how much activity can be crushed and how much the crushing process costs. Hence, we must ask the following information. The first one is activity cost under the normal or expected activity time. The second one is time to complete the activity under maximum crushing time, the shortest possible activity time. The third one is activity cost under maximum crushing. Let T sub I is equal to the expected time of for activity I, and T sub I is equal to the time for activity I under maximum crushing. M sub I is equal to maximum possible reduction in time for activity and due to crushing. Given expected time for activity I and time for activity I under maximum crushing, we can compute maximum possible reduction in time for activity I due to crushing. Next, let's see denote the cost for activity I under the normal or expected activity time, and let's see sub I denote the cost for activity I under maximum crashing. Thus, per unit of time sample per day, the crashing cost P for each activity is given by K sub I is equal to C sub I minus C sub I over M sub I. For example, if the normal or expected time for activity A is 7 days at a cost of C sub A is equal to $500 and the time under maximum crashing is 4 days at a cost of C sub A is equal to $800. Equation 9.6 and 9.7 shows the that the maximum possible reduction in time for activity A is M sub A is equal to 7 minus 4 is equal to 3 days, with crushing cost of K sub A 800 minus 500 is equal to 300 over 3 is equal to $100 per day. We make the assumption that any portion or fraction of the activity crash time can be achieved for a corresponding portion of the activity crashing cost. For example, if we decide to crash activity A by only 1.5 days, the added cost would be 1.5 or $100 is equal to $150, which result in a total activity cost of $500 plus 150 is equal to $650. In figure 9.15 shows the graph of the time-cost relationship for activity A. The complete normal and crash activity data for the two machines maintenance project are given in table 9.10, which activity should be crashed and by how much to meet the 10-day project completion deadline at minimum cost. Activity A has the lowest crushing cost per day of the three, and the crushing this activity by 2 days will reduce the ABA path to the desired 10 days. Keep in mind, however, that as you crush the current critical activities, other paths may become critical. Thus, you will need to check the critical path in the revised network and perhaps either identify additional activities to crash or modify your initial crossing decision. For a small network, this trial and error approach can be used to make crashing decisions. In larger networks, however, a mathematical procedure is required to determine the optimal crashing decision. The next one is linear programming for crashing. Let us describe how linear programming can be used to solve the network crashing problem with program evaluation and review technique, critical path method. We know that when an activity starts at its earliest start time, then finish time is equal to earliest start time plus activity time. However, if slack time is associated with an activity, then the activity need not start at its earliest start time. In case we may have finish times greater than earliest time plus activity time because we do not know ahead of time whether an activity will start at its earliest start time. We use the following inequality to show general relationship among finish time, earliest start time, and activity time for each activity. Finish time greater than or equal earliest time plus activity time. Consider activity A which has an expected time of 7 days. Let x sub A is equal to the finish time for activity A and y sub A is the amount of activity A is crashed. If we assume that the project begins at time 0, the earliest start time for activity A is 0 because the time for activity A is reduced by the amount of time that actually A is crashed and finished For activity A must satisfy the relationship x sub A is greater than or equal 0 plus 7 minus y sub A. Removing y sub A to the left side, A x sub A plus y sub A is greater than or equal to 7. In general, let x sub I the finish time for activity I, y sub I the amount of time activity I is crushed. If we follow the same approach that we use for activity A, the constraint corresponding to the finish time for activity C expected time is equal to 6 days is x, x sub C greater than or equal 0 plus x minus y sub C or x sub C plus y sub C greater than equal 6. Continuing with the constraint pass of PERT CPM procedure, we see that the earliest start time for activity B is x sub A, the finish time for activity A. Thus, the constraint corresponding to the finish time for activity P is x sub B greater than or equal x sub A plus 3 minus y sub B, or x sub B plus y sub B minus x sub A is greater than or equal 3. Similarly, we obtain constraint for the finish time for activity D. Finally, we consider activity E. The earliest start time for activity E equals the largest of finish time for activity B and D, because the finish time for both B and D will determine by the crushing procedure. We must write two constraints for activity E on base of the finish time for activity B and one based for the finish time for activity D. Recall that the current production levels made completing the maintenance project within 10 days imperative that the constraint for the finish time for activity E is x sub E less than or equal 10. In addition, we must add the following 5 constraints corresponding to the maximum allowable crashing time for each activity: y sub A less than or equal 3, y sub B less than or equal 1, y sub C less than or equal 2, y sub C less than or equal 2, and y sub E less than or equal 1. As with the linear programs, we add the usual non-negative requirements for decision variables. All that remains is to develop an objective function for the model. However, the total project cost for a normal completion time is fixed at $1,700. We can minimize the total project normal cost plus crushing cost by minimizing the total crushing cost. Thus, the linear programming objective function becomes mm, y 100 y sub A plus 150 y sub B plus 200 y sub C plus 150 y sub D plus 250 y sub E. Thus, to determine the optimal crushing for each activity, we must solve a 10-variable, 12-constraint linear programming model. The optimization software such as Excel Solver provide the optimal solution of crushing activity by 1 day and activity E by 1 day. With the total crushing cost of $100 plus 250 is equal to 350, with a minimum cost crushing solution, the activity times are as follows. The linear programming solution provided the revised activity times but not the revised earliest start time, latest start time, and slack information. The revised activity times and the usual PERT ITCPM procedure must use to develop the activity schedule for the project. Thank you.